Well, welcome back to chapter 6, part 2. We're going to talk about something called free energy and how energy changes in this part. So, the first concept that we're going to talk about is that we measure energy, we measure free energy to help us understand chemical reactions. And we're going to see graphs like this one a lot coming up, and we're going to really analyze it. But I like this cartoon to start out with because the idea of this rock has more potential energy than this rock, but sometimes it's hard to get that energy to be released. You got to push it up a little hill first, and then it releases its energy. So that's the big concept that we're going to be dealing with. Some people think that free energy is like, the solar panels or these energy generators that don't take a lot of effort because they seem to create their own. That's not what we're talking about here. In biology, we're talking about the part of the system's energy that can do work, considering when temperature and pressure are uniform throughout, like what happens in a living cell. So free energy change, we symbolically refer to that as delta G. That's the symbol for change of free energy. And we're going to be talking about change in free energy, stability, and equilibrium. So again, the change in the amount of free energy, that's delta G. And that triangle shape is the delta sign in Greek. So delta G, the change in free energy during a chemical reaction is the difference. So we're doing some subtraction here, right? It's the difference between the free energy of the final state and the free energy of the initial state. So this little equation here, delta G is equal to the energy in the final state minus the free energy of the initial state. Only reactions that have a negative delta G are spontaneous, kind of like this, right? If you subtract this from this, then you get a negative delta G, if you can kind of imagine that happening. So again, going back here, this has less free energy, this has more free energy, and so you get a negative number when you subtract this from this. So that's spontaneous. We'll talk about that little hill that you got to get over in a little bit. But spontaneous reactions can be harnessed by the cells to do cellular work. And we'll give you some examples of what cellular work are in a minute. So again, free energy is a measure of a system's instability, its tendency to change to a more stable system, a more stable state. When you're going through a free energy change, the free energy decreases and the stability of a system increases. When that rock gets down to the bottom of the hill, it's a much more stable system. Unstable systems that have a higher G tend to change so that they become more stable, having a lower G over time. Let's take a look at some quick examples, some of which you're already familiar with. So at the top here, we have a system that has higher G. It's got higher free energy, it's less stable, but there's a greater capacity to do work. That's true in all of these examples. The person at the top of the diving board, it's also true when molecules are tightly close together, like as in diffusion, where they go less close together. And it's also true in chemical reactions where one molecule can be broken down into lots of subparts. So in the spontaneous change, going from where it's more free energy and less stable, the delta G, we say, is less than 0. That means it's negative. The system becomes more stable over time, and energy is released to do work. So gravitation, diffusion, chemical reactions, all of these are examples of how free energy is used it changes state. Eventually, you're going to get to something called chemical equilibrium. And chemical equilibrium, the forward and reverse reactions occur at the same rate. So it's like as stable as you're ever going to get if a chemical reaction is going forward as well as in reverse. So it's a process, it's spontaneous, and it can perform work only when it's moving towards equilibrium. Once a system is at equilibrium, you really can't do any work anymore. This can be applied to chemistry, can be applied to lots of things, but we're going to really focus on the biological aspects of this, including concepts of exergonic and endergonic reactions. Now, exergonic reactions proceed with a net release of free energy. It's spontaneous. Delta G is negative. The magnitude, that means like the difference between the products and the reactants, the energy found there, we say that's the magnitude of the delta G. That represents the most amount of work you can get out of the system to perform any specific kind of work. In an endergonic reaction, this is where a system needs to absorb energy in order for you to go from the reactant to the product. It's not spontaneous. Delta G is positive, and that means you got to add energy into the system. The magnitude, again, the difference between the products and the reactants, the magnitude of this height here, that tells you how much energy is required. And in this case, the delta G is greater than 0, so it's a positive number. The words endergonic and exergonic do tell you something about what's happening. So ender is like endocytosis, like exer is like exocytosis. So with exergonic reactions, energy is exiting the system, and with endergonic reactions, energy is entering the system. A nice example of how to think about these reactions we can see in an example of a hydroelectric system. I don't know if you're familiar with hydroelectric dams, but you probably have seen water wheels, and that's somewhat similar to a hydroelectric dam. Hydroelectric systems are great analogies. So think about the amount of water that's on this side of the dam, this side of the turbine right here, the thing that's turning. And the reason this is turning is because water is being forced down this hill and it's turning the wheel in this direction. That wheel turning is creating electricity to power a light source. So just by having it go downhill, like an exergonic reaction, it's allowed to turn that turbine and generate electricity. Once you get to equilibrium, that's delta G is equal to 0. The water is not being forced down anymore. It's equal. Maybe some of the water molecules on this side are going to move to that side and vice versa, but that's not enough energy to turn that wheel. So at equilibrium, work can no longer be done. Cells are not in equilibrium. Cells are open systems, and so they're constantly experiencing a flow of materials into the cell and out of the cell. It's like from the previous example, if you opened up the top and let a water supply come in, that water would be constantly adding on this side, constantly flowing down the hill, constantly turning the turbine, and then a little outflow at this side. So that's what a great example of what an open system is. And cells are open systems. The fact that metabolism as a whole inside your body is never at equilibrium is like one of the absolute defining features of life. You've got to be an open system if you're going to stay alive. When we talked about pathways earlier, and this is a great example of how if you hook several of these hydroelectric dam turbine systems together, you can use one to power the next reaction in the system, and you get a nice little chain reaction going on. So remember, we used the term catabolic pathway earlier. Catabolic pathways in cells release free energy in a series of reactions, just like we got our input, so we're an open system, turning this turbine, it's going downhill, turning this turbine, it's going downhill, and so forth and so on. That's a multi-step hydroelectric dam. That's what our That's what our metabolic pathways look like. The product of each reaction is the reactant for the next step, and that prevents the system from reaching equilibrium. I know that was pretty short, but sometimes short is sweet, and so we are going to stop this video, and you can join me in part 3 in just a minute.